team formed by Alejandro, Alfredo, Fran, Marcos, Martin, Oscar, Javi, Oscar, Xavi, and last but not least, Oscar.
And the main purpose of this video is to illustrate what aerodynamic phenomena takes place under an F1 car. In order to show how this modern floor of an F1 car works, we will briefly explain Bernoulli's principle and Coanda effect.
Then we will talk about proposing phenomena and ground effect and its relevance around the last years and know what it is.
To continue, we will show a CFD simulation of an F1 model.
And finally, we will proceed with the experiment where we will analyze a 3D printed model similar to the model form of a F1 car. And we will compare the theoretical result with the one obtained in the wild type.
Bernoulli equation is a result of energy conservation applied to fluids. It's composed of three terms: static pressure, referring to internal energy, dynamic pressure or kinetic energy, and hydrostatic pressure or potential energy. Bernoulli equation states that in a steady, incompressible, 1D, no-loss fluid, the sum of these three terms is constant. For instance, in a Venturi tube, the pressure decreases in the small cross-section due to the increase of velocity. Similarly, in a vertical tube, the pressure at the top reaches its lowest.
We all know that when a solid hits the surface by Newton's action-reaction law, it bounces in the other way. But this behavior changes in fluids. When a fluid stream goes over a slightly curved surface, due to viscous forces, some of the particles below the stream near the curved surface are drawn into the stream, creating a low pressure zone under the stream and near the surface. This difference of pressure between the upper and lower parts of the surface will exert a net force pushing the stream downwards, adapting it to the shape of the curve. This is what we call Coanda effect. This is exactly what it is being represented on the animation, applied to a circular section where it can be seen how the horizontal inciding stream changes its trajectory and adapts to the curvature.
In this case, the hairdryer generates a flow between the balloons, reducing the pressure. A greater pressure distribution on the outer part pushes the balloons inwards. Due to Coanda effect, the particles gather below the can. This creates a high pressure zone that moves the can outside the glass.
With just water and a spoon, we can clearly see Coanda effect. This is the same example we were looking at a minute ago. A very clear example of the Coanda effect can be seen in the experiment. The flow caused by the hairdryer gets curved and adapts to the surface of the ball, leaving it in a steady position. Such strong the effect is that even if the hairdryer is tilted almost 60 degrees, the ball is still in equilibrium.
Up to the early 60s, engineers only focused on making cars streamlined and minimizing drag. However, as vehicles became faster, they started to become very unstable. The Lotus 49 was the first attempt to solve this problem. With its new inverted front wing, it completely revolutionized Formula One aerodynamics. The most notable example of round effect evolution also came from the Lotus team. The Lotus 78, with its wide, low-slung body and side skids, effectively sealed off the underbody, allowing it to generate significant grip. Additionally, other original ideas included using a fan to suck the air behind the car, as the Brabham team did during this period. Eventually, the FIA banned most of these techniques due to safety reasons. New round effect strategies aim to use floors like the one we are studying in this video.
The ground effect in race cars is caused due to how the flow interacts with the aerodynamic surfaces of the car, but more importantly on the floor. The floor generates a high pressure zone and a low pressure zone just under the car. This happens thanks to the Venturi channels and the geometry of the floor of the car, which are responsible of lowering the pressure and accelerating the flow. This accelerated flow generates a force called downforce, which is actually pushing the car into the floor and giving some extra speed to the car. Here we can see what happens when the car doesn't generate enough downforce. When a lot of downforce is generated, a phenomenon called porpoising occurs. This porpoising means that the car starts bouncing and the floor of the car is touching the ground with a certain period, making the car so difficult to control for the pilot.
We've also done a simulation, a CFD simulation, and for it we've used OpenFOAM, and we are opening it in parallel First to say that we didn't have the resources and our computer wasn't so powerful so that we could get mesh independence or volume independence. So for this reason, we just calculated a simplified mesh that wouldn't take so much time and didn't have so many blocks. The density we used is 1.225 kilograms per meter square, and the velocities are the following ones.
Corresponding the blue color to a lower velocity, it can be seen that the expected profile was almost achieved. The velocity increases in the middle section, but due to the lack of diffuser, the velocity is still very high at the exit.
Here we can see the car performed, and this is the distribution of pressures in the car.
It is important to take into consideration that when working with open flow, when we calculate the pressure, indeed we are getting the dynamic pressure. That it's the coefficient between the relative pressure and the density. These are the values that we have used for the simulation, and even though compressible flow may appear, we've simulated it considering only incompressible to simplify the result.
Here we can see the graph of the velocity. The length of the car goes from here to here. As we can see, when the air enters the floor, there is an acceleration of the flow, and then when the air goes to the floor of the car, there is a big decrease in the velocity. All in all, the pressure distributions correspond to our assumptions, except for a peak that occurs due to missing sealing fins of the chosen cut.
In order to put into practice what we mentioned before, we designed this 3D piece.
The CAD design of the floor was downloaded from a 3D online repository. Some changes had to be done in order to prepare it for the wind tunnel. It was scaled to a 15% of the original size and cut in half. Also, a M6 thread was performed so it could be held in the wind tunnel, and finally 16 intakes were added in order to connect the floor to the manometric table. Also, some minor changes in the thickness to improve the quality of the impression were done.
Another important function of the floor is to seal the low pressure zone inside it from the high pressure zone outside the floor. This is done with the fins and the vortex generators around the edges, which create a vortex which separates this zone like a dividing wall. This was the same procedure that the old skirt did. Also, the diffuser, apart from decreasing the speed of the flow, it changed the direction of the flow upwards, so the turbulent air created doesn't affect the car following behind.
Securing the piece in the tunnel was a difficult task. It was attached to the upper part of the tunnel with a height difference between the wall and the piece of 3 mm, as in the real Formula 1 cars. Following a similar procedure as in the lab session 3, different measures were taken for the velocities as seen in the following graph. Point 1 and 2 correspond to the intake of the floor, where the flow decreases its velocity due to the impact with the entry. From point 3 to 6, we have the smaller section achieving a low pressure.
The last points correspond to the diffuser, where the pressure starts to increase again. It can be observed that the higher the velocity, the greater the pressure difference achieved. The velocity was limited to 20 meters per second, as there was a risk of breaking the piece, which happened at the end, meaning that it was impossible to achieve the high velocities of real racing cars. Nevertheless, it was demonstrated that the 3D print fulfills its purpose, as the expected tendency appears.
Weighing all the process done so far, it can be said that this race to demonstrate the effect of an F1 floor to its aerodynamic and overall performance was pretty challenging but also gratifying. In this multidisciplinary process where no idea was big enough, we had a lot of pitfalls, but we always managed to get back up again. We only have to see where we started versus what we ended up with. We learned to implement the different knowledge acquired on the lab sessions, such as measuring on a wind tunnel or reading the values from a manometric table. We also learned how the devil relies on the details, as we needed to smooth the surface of a 3D printing with a Dremel, as we know that any imperfection could affect the final results. I could give you 33 more reasons of real-life knowledge that we acquired. Nevertheless, the important aspect is that the desired effect was observed, and we can only imagine the magnitude of downforce that an actual Formula 1 car could achieve at higher speeds. Now that we are arriving to the checkered flag of this video, we like to thank the few people that helped us during this journey, giving a special thank you to Andres Teixeira and his CMT group, and also to Horus for letting us use their 3D printer. We hope you learn as much as we did with this video and that you also enjoy it. Have a good one.